look at a standard map of the world. We are conditioned to think of the ground beneath our feet as permanent and stationary, but if you look closely at the edges of the map, it begins to look far less solid. Look at the east coast of South America and the west coast of Africa. They don't just look similar, they fit together perfectly, as if they were once parts of a single, larger whole. This raises a question that sat unanswered for centuries. Why do these continents look like a broken jigsaw puzzle? And what force is strong enough to pull them across the globe? In 1912, a German meteorologist named Alfred Wegener looked at these coasts and saw something the scientific establishment was ignoring. He called his proposal continental drift. Wegener argued that 200 million years ago, all the land we know today was merged into one massive supercontinent called Pangaea, meaning all Earth. According to his model, this single continent was entirely surrounded by a lone global ocean known as PANTHALASSA. Most scientists at the time found the idea impossible. Wegener could describe the what, but he couldn't explain the how. He had no physical mechanism that could push an entire continent through the solid floor of the ocean. He suggested the Earth's rotation or tidal forces might be responsible, but the physics didn't add up. Because he lacked a viable engine to drive the movement, his theory was largely dismissed, and the mystery of the matching coastlines remained a stagnant curiosity. Even without a mechanism, the physical evidence Wegener gathered was difficult to explain away. The shoreline match was only the beginning. The fossil record provided a definitive link. Remains of the Mesosaurus, a small reptile adapted to freshwater, are found in only two specific places: the southern Cape of South Africa and the Irovera formations of Brazil. There is no biological path for a freshwater animal to cross the 4,800 kilometers of saltwater that now separates those 2 points. Further proof came from the rocks themselves. Geologists found thick layers of tellite, sediment left behind by glaciers, in India, Africa, and Australia. These are places that are now tropical or arid, but their geological history is identical. The data suggested that the Earth had a way of relocating land over vast distances. But science would have to wait for the arrival of new technology to find the engine that made it possible. Following World War II, a new era of exploration began as oceanographers started mapping the deep ocean floor for the first time. They discovered that the seafloor wasn't a flat, featureless plain. Instead, it was dominated by the mid-oceanic ridges, the longest mountain chains on the planet, hidden entirely underwater. In 1961, geologist Harry Hess proposed that these ridges were actually active volcanic sites where new molten lava was constantly rising to the surface. Hess realized that as this lava cools and hardens into new crust, it wedges into the ridge and pushes the existing ocean floor outward. He called it seafloor spreading. This was the mechanism Wegener had been missing. The continents weren't drifting through the ocean floor itself was growing, acting as a conveyor belt that carried the continents along with it. By 1967, these ideas formed the theory of plate tectonics. It showed that the Earth's outer shell is actually broken into 7 major plates that move as rigid units over a softer layer beneath. The engine driving this is in the mantle. Heated rock becomes soft, rising toward the surface in a rolling motion called a convection current. Powered by intense heat from the core, this material spreads out beneath the plates, dragging them along. This explains the activity at plate boundaries. Some plates pull apart to create new crust, while others crash together, forcing one plate to sink back into the mantle to be consumed. We now know that continents are passengers on a massive rocky conveyor belt, constantly rearranged by the heat circulating deep within our planet. To see this engine in action, we can look at the Indian plate. 200 million years ago, India was a large island situated off the coast of Australia, thousands of miles from where it sits today. After Pangaea broke apart, India began a rapid northward journey across the ancient Tethys Sea, moving toward the Asian continent. About 40 to 50 million years ago, the Indian plate slammed into the Eurasian plate. The force of that collision was enough to buckle the Earth's crust until it reached 5 miles into the sky. This massive tectonic collision is what created the Himalayas. The sheer height and scale of these peaks are the direct results of two plates continuing to grind into one another with immense pressure. The process that built these mountains never stopped. Because the Indian Plate is still pushing northward today, the Himalayas are actively growing taller by several millimeters each year. We perceive the ground as solid and stable enough to build our cities and our lives, but that stability is a matter of perspective. Beneath the surface, the planet is in a state of constant, slow-motion transition. The world map is not a finished document. It is a moving puzzle powered by internal heat that is constantly redrawing the face of the Earth. To explore more of the hidden systems that shape our world, subscribe and join us for the next investigation.